intermolecular hydrogen bonding in which all cases we can observe? In water molecules. Intermolecular hydrogen bonding can be observed in water molecules. Like this, it will continue. These are same type. Next one between alcohols and water also. Like this. This is intermolecular hydrogen bonds will form. Hydrogen bonds, nothing but dipole-dipole attractions are there. Now, little more than dipole-dipole attractions. Polar bonds are there now. Yeah, little more polarity. If it is more, hydrogen bonding will see. Next one, intramolecular hydrogen bonding. First of all, properties of intermolecular hydrogen bondings. Instead of telling properties, which and all effects are there with the intermolecular hydrogen bonding, I will tell you. Intermolecular hydrogen bonding increases boiling point. If any molecule has intermolecular hydrogen bonding, its boiling point will be high compared to other compounds. So alcohols are having high boiling points compared to hydrocarbons or ethers of comparable molecular masses. Wherever hydrogen bonding increases, more forces of attractions also increases, surface area increases. So we need to apply more energy to break the attractions. Okay, intermolecular hydrogen bonding. Boiling points of the compounds. Presence of intermolecular hydrogen bonding increases boiling point. And actually alcohols are organic compounds. Generally organic compounds will not soluble in inorganic solvents, but alcohols can soluble in water. Reason is alcohols can form intermolecular hydrogen bondings. Alcohols can form intermolecular hydrogen bonding. If any molecule forms intermolecular hydrogen bonding, its solubility is more. So intermolecular hydrogen bonding also increases boiling point. Intermolecular hydrogen bonding also increases boiling point of the compound. And solubilities also. If they form in they have more forces of attraction. Sorry, I explained solubility now. No problem. Boiling point also increases. Intermolecular hydrogen bonding increases boiling point. Forces of attractions increases and surface area increases. One more is solubility effect. Solubility of organic compounds soluble in organic solvents, inorganic compounds soluble in inorganic solvent generally. But here alcohols, they are organic compounds, but they are soluble in water. Reason is alcohols can form intermolecular hydrogen bonding with water. Alcohols can soluble, carboxylic acids can soluble. Okay? If they form intermolecular hydrogen bondings, they can soluble in water with the So from this, what we can say, alcohols increases solubility also. Presence of internal alcohol. Examples: alcohols and carboxylic acids. They can form hydrogen bonding with water, so they are soluble in water. Intramolecular hydrogen bond. Intramolecular hydrogen bond. Intramolecular hydrogen bond. Intramolecular hydrogen bond. If hydrogen bond form within the molecule, this happens within the molecule. Within the molecule. Example, if you see orthonitrophenol. This is called phenol, benzene with the OH group, phenol. Names, if you don't know, leave it, student, nothing is there. I'll write here. You are in, for timing, try to understand what is hydrogen bonding. Here, hydrogen, oxygen are very close, so they can form hydrogen bonding. It is only one molecule. It is only one molecule. Earlier, is formed in between two molecules, in between two or more molecules of same or different types. Here within the molecule, it is within the molecule, right? So this bonding is called intramolecular hydrogen bonding. Example for intramolecular hydrogen bonding, orthonitrophenol. This is phenol. Next, very next to the substituent, whatever the position is there, that is called orthonitrophenol. Phenol. And other compounds are there. Names and all you don't know, so I am not giving. Salicylaldehyde and all, they can form intramolecular hydrogen bonding. See students, if intramolecular hydrogen bonding is there in any compound, compound will form closed structure. Compound intermolecular, it is forming open structure and forming long chains. It is increasing the surface area. In case of intramolecular hydrogen bonding, it is decreasing the surface area by forming closed structures. So boiling point decreases. So because of intramolecular hydrogen bonding, boiling point decreases. Boiling points mainly depends on molar mass and van der Waals forces of attractions. If surface area is less, van der Waals forces of attractions will be less. If van der Waals forces of attractions are less, boiling points will be less. Okay, so intramolecular hydrogen bonding decreases the boiling point. Intermolecular hydrogen bonding increases the boiling point by increasing surface area. So boiling point decrease. Molecules which are having intramolecular hydrogen bonding, their boiling points are less compared to other compounds. Example, if I take here, orthonitrophenol has intramolecular hydrogen bonding. Exactly opposite position to this phenol, OH group is there, and this is called para position. In para position, nitro group is there. This hydrogen bonding is not possible. Intramolecular is not possible. So there has to form intermolecular. Intermolecular. That time, two molecules you have to take. like this. So here it is increasing in surface area. If you observe the molecules properly, you can understand easily. So like this, it will continue long chain. So this is called paranitrophenol. These are like isomers only. Paranitrophenol. Para position nitro group is there. Here ortho position nitro group is there. So if any substituent is there, students, so timing you just follow this. This is the substituent. Substituent. The substituent very next position is called ortho position. This one also ortho only. Ortho next is called meta. This is meta position. This one also meta only. Exactly opposite means 180 degrees. If you find out, it is para position. So here nitro group is presented para position with respect to the main substituent. Here it is ortho substituent. Sometimes they are asking out of orthonitrophenol and paranitrophenol, which is steam volatile. Steam volatile means easily it evaporates. Orthonitrophenol. Sometimes they are only giving orthonitrophenol is steam volatile, paranitrophenol is not steam volatile. Reason they are asking. So orthonitrophenol, in orthonitrophenol, intramolecular hydrogen bonding exists. In paranitrophenol, intermolecular hydrogen bonding exists. So boiling point of O nitrophenol. This we can write simply O is less than P nitrophenol. P nitrophenol. Chemical bonding. Last concept is molecular orbital theory, and very very important also. Molecular orbital theory. According to this theory and this molecular orbital property, everything somewhat clearly explained by LCAO. LCAO. LCAO is nothing but linear combination of atomic orbitals. The full form of LCAO, linear combination of atomic orbitals. Linear combination of atomic orbitals. So according to this concept, while forming molecular orbitals, atomic orbitals undergo overlapping. Atomic orbitals undergo overlapping. So here, atomic orbitals they represented with psi A, psi B. Atomic orbitals they represented with psi A and psi B. Psi is the wave function. Which gives the information about probability of finding electron. Probability of finding electron where it is maximum. So here, while these atomic orbitals, when they combine, while forming molecular orbital, they come like this. They can form two types of molecular orbitals. One is anti-bonding molecular orbitals. Another one, bonding molecular orbitals. When they combine, they form bonding molecular orbital like this. If they are not combining, when proper orientation is not there, proper symmetry is not there, then anti-bonding molecular orbitals also we can expect. When two atomic orbitals combine, according to LCAO, when two atomic orbitals combine, they can form two molecular orbitals like hybridization only. How many atomic orbitals are involved in hybridization? how many atomic orbitals are intermixing, so many hybrid orbitals will get. Same thing here. When two atomic orbitals combine linearly, they can produce two types of molecular orbitals, two molecular orbitals. In that, one is bonding molecular orbital, another one is anti-bonding molecular orbital. Two types of molecular orbitals will produce bonding molecular orbital and anti-bonding molecular orbital. Now here bond forms, so it is bonding molecular orbital. It's only for understanding purpose. In for little information I'm giving. First year you will get more information about this. But main topics I'll give everything. These are not so important, only for understanding the concept. This one called anti-bonding molecular orbitals. Anti-bonding molecular orbitals. Anti-bonding molecular orbitals. When two atomic orbitals combine, form sun. And one more thing, students. Suppose this one I am taking psi A, this one is psi B. When they form molecular orbitals, we'll write summation of those orbitals, psi A plus psi B. If they form anti-bonding molecular orbitals, it will be psi A minus psi B. Okay. When two atomic orbitals combine, approach each other. I told you, two combinations we can observe. Psi A minus psi B. They are away from each other. They are repelling each other. Psi A plus psi B. They are combining, attracting each other. Okay. These are called anti-bonding molecular orbital ABMO, BMO. Bonding molecular orbitals. How many atomic orbitals combine? So many molecular orbitals will get. Now, according to you, so they will have less energy or not. If bonding is not correct, anti-bonding is correct. No. In that way, he guessed, I think. Okay. Anti-bonding molecular orbitals are having more energy. Anti-bonding molecular orbitals are having more energy. Reason is they are repelling each other. So in that repulsions, they go to higher energy state. Once if they form bond, they lose energy. Bond formation or bonding formation of bonding molecular orbitals, it is like exothermic process. They lose energy. So bonding molecular energy of bonding molecular orbital is less than anti-bonding molecular orbital. Understood, students? Bonding molecular orbital, they are forming bond. If they form bond, they lose energy. If they lose this one anti-bonding molecular orbitals, they are having repulsions, so they go to higher energy state. They gain higher energy. Clear, students? Energy of anti-bonding molecular orbital is greater than bonding molecular orbitals. Next one, this bonding anti-bonding molecular orbitals. Here, molecular orbitals represented with sigma 1s, sigma 2s, pi 2px, pi 2py, sigma 2pz. These are bonding molecular orbitals representation. For this anti-bonding, if you want to write, just keep star. Sigma star 1s, sigma star 2s, pi star 2px, pi star 2py, sigma star 2pz. These are anti-bonding molecular orbitals. anti-bonding molecular orbitals. Okay, these are the representations of bonding molecular orbitals and anti-bonding molecular orbitals. Writing electronic configuration is there in case of atoms 1s, 2s. Same way here, molecular orbital energy order also we can write. But here there are two orders, up to 14 electrons, one order, energy order of bonding molecular orbitals. Sorry, molecular orbitals. It is easy, students. Beginning this synopsis and all, you may get little confusion beginning, but easy it is. Nothing is there. While doing applications, you can understand better than this. Molecular orbitals. Energy order. Energy order. Here there are two systems, students. Up to 14 electron system. 14 electron systems. Energy order is sigma 1s is less than sigma star 1s, less than sigma 2s, less than sigma star 2s. Next, pi 2px is equal to pi 2py. Next, sigma 2pz. Next, pi star 2px is equal to pi star 2py. Don't worry, students, I'll tell you how to remember also. Sigma star 2pz. Sigma star 2pz. This is the molecular orbital energy order. Molecular orbitals energy order. See, students, sigma 1s, sigma star 1s easy only. Sigma 2s, sigma star 2s easy only. Afterwards, remember x, y, z. X, Y, Z. X, Y, Z. And remember, pi bond is formed by X and Y. Better to keep that representation. Pi bond is formed by XY only. Sigma bond is formed by Z. Generally, Z will be along the internuclear axis, so it forms always sigma bond. So in that way, you keep. So pi to px, pi to py, and here equal to I put equal. These two orbitals are having same energy. These two orbitals are having same energy. These two orbitals are having same energy. Then these are called degenerate orbitals. Degenerate orbitals. Degenerate orbitals. Srivani, still you need or this much is enough? Screen. Okay. Okay, degenerate orbitals. What is the meaning of degenerate orbitals? Orbitals which are having same energy. Orbitals which are having same energy are called degenerate orbitals. Like atomic orbitals, 3p orbitals, how they are having same energy. Here molecular orbitals are also having, but here two orbitals only having same energy. Understood, students? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then x, y, z. Pi to px is equal to pi to py. X and y are equal. Then sigma to pz. After writing, again you go for x star, y star, z star. X star, y star, z star. That order you follow. Easy it is. And afterwards, I'll give one simple technique without using this only. But theoretically, we have to learn, no, so I'm giving. Next one, above 14 electron system. above 14 electron system. Nothing is there, students. Sigma 1 is, if you know above 1, this one is easy only. Next one, this will come friend. So sigma 2pz will come friend. Afterwards, the rest of the order is same. Then 5 star 2px is equal to 5 star 2py. So far in molecular orbital theory, what I taught students, molecular molecular orbitals formed by the combination of atomic orbitals. How many atomic orbitals combine? So many molecular orbitals will form. If two atomic orbitals combine, form two molecular orbitals. In that, one is bonding molecular orbital, another one is anti-bonding molecular orbital. Equal number of bonding and anti-bonding molecular orbitals will be found. And one more point, what did I say? Since bonding molecular orbitals forming bond, their energy is lower. Anti-bonding molecular orbitals, they are not forming bond since repulsion occurs, so their energies are high. Anti-bonding molecular orbitals energies are high. And if we compare the energy orders of different molecular orbitals, it follows up to 14 electron system. One way it follows, above 14 electron system, one order it follows. Now we'll apply energy orders. We know how to arrange the electrons. We'll see. Suppose here, simple molecule I will take, carbon C2 molecule I will take. C2 molecule. In my carbon atomic number, you know, 6. C2 means it has, now C2 means two carbons, no? C2 contains 12 electrons. 12 electrons. These 12 electrons means it is up to 14 electron system only. Arrange electrons, and here in according to LCO, each molecular orbital capacity is 2 only. Maximum capacity of each molecular orbital is equal to 2. We can accommodate only 2 electrons in each molecular orbital. So now I'll arrange these 12 electrons in 12 electrons in orbitals. One up to 14 electron system. No, sigma 1s 2 electrons, sigma star 1s 2 electrons, sigma 2s 2 electrons, sigma star 2s 2 electrons, 2, 2, 1, 2, 3, 4, 5, 6. Total how many? 12 electrons arranged. 12 electrons. 1, 2, 3, 4, 5, 6. 12 electrons. These 12 electrons we arranged. What are the advantages of this? We can find out bond order. We can find out magnetic nature also. To find out bond order, I am giving formula, students. Bond order is equal to how many bonds are existing between two atoms in a molecule. We can find out. Bond order formula is half into number of bonding electrons minus number of anti-bonding electrons. Number of bonding, NB is nothing but number of bonding electrons. Important, students. Bonding electrons. Na is nothing but number of anti-bonding electrons. Number of bonding electrons and number of anti-bonding electrons. Half into 1, 2, without star bonding electrons, with star anti-bonding electron, that you know already the representation. Here 1, 2, 3, 4. 4 twos are 8. 8 bonding electrons. Next with star, only 2 are there. 2 twos are 4. In sigma star, 1s, 2 electrons are there. In sigma star, 2s, 2 electrons are there. 8 minus 4 by 2 is nothing but 2. So in between, in C2 molecule, there are 2 bonds. So its bond order is C double bond C. And how to find out? How to find out magnetic nature, students? Magnetic nature. Bond order is 2. Magnetic nature. If any orbital contain at least one orbital contain single electron, it is paramagnetic. Otherwise, diamagnetic. If all the orbitals contain two electrons, it is diamagnetic. If any one orbital contains single electron, then it is paramagnetic. Okay. Now tell me, students, is it diamagnetic or paramagnetic? Observe the electronic configuration and tell me. Magnetic nature. If all the orbitals get two electrons, diamagnetic. If any unpaired, means single electron is there in orbital, it is paramagnetic. Is it paramagnetic or diamagnetic? Tripti, correct answer. Only one student answered. I only told. Diamagnetic. JR batch, what happened to you? You were not like earlier. You were not like earlier student. When I was explaining GOC, you did better. Actually, this is easier than GOC. I'm not getting good response. I don't know what happened. And you are not telling this, you explain that, you are not asking also. No response from you. Single, if any orbital contains single electron, paramagnetic I said. Can't you see single electron in orbital? Here one is there or two is there, can't you see? In this any orbital, single electron is there. Should I teach 1 and 2 numbers? 1, 2, 3 numbers? Then what? Sandra, now you are giving answer. I told clearly, if any orbital contains single electron, only one electron, paramagnetic. At least one orbital, if it contains single electron, paramagnetic. If all the orbitals contain two electrons, two number only I said. I didn't tell paired up also. Still, I didn't get response. At least one. Paramagnetic. At least one, or it can be more also. So here, in this electronic configuration, no orbital has single electron, so it is diamagnetic. Diamagnetic. Can you find out the bond order N2 students? Nitrogen atomic number 7. N2 means how much? 14. Can you find out? Write the electronic configuration and find out the bond order. Sandra, correct answer. Avani, correct answer. Very good. Tripti, correct. So here, nitrogen 14 electrons, no? Sigma 1s 2 electrons. Sigma star 1s2 2 electrons. Sigma 2s2 2 electrons. Sigma star 2s2 2 electrons. Pi 2px is equal to pi 2py. So here are 2 electrons, here 2 electrons. 1, 2, 3, 4, 5, 6. Still 2 more electrons are there. Sigma 2p is a 2. Okay. Now, to find out bond order, what formula is there? Of number of into number of bonding. 2, 3, 4, 5. 5 2s are 10. Minus antibonding 1, 2. 2 2s are 4. So 6 by 4, 2 means 3. Bond order is 3. N triple bond N. Tanmay, so much you don't type, just send answer. Bond order is enough. It is very difficult to type all those things. And next, shall we go to O2 molecule? O2 molecule. O atomic number is 8. So O2 contains 16 electrons. Oxygen atom contains 8 electrons. Molecule contains 2 into 8, 16 electrons. 16 electrons arrange. So it is above 14 electron system. Energy order will change. Above 14 electron system, right? Energy order will change. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then sigma 2pz will come first. 2. Next, pi star pi 2px is equal to pi 2py. 1, 2, 3, 4, 5, 6, 7. 14 over. Next, energy order is pi star 2px is equal to pi star 2py. See students, 14 electrons till here. Now 2 more electrons are there. In that case, 2 electrons you are not supposed to give to one orbital. Since these are degenerate orbitals, we have to give one electron. Same Pauli's rule, Aufbau's rule, Hund's rule follows. Here all molecular orbitals also follows all those 3 conditions. In case of degenerate orbitals, one electron should be given to each orbital. If electrons are there excess, then only pairing takes place. Excess electrons are there, then pairing takes place. So 2 electrons are there. 2 degenerate orbitals are there. So one electron should be given to each orbital. Now come to the bond order. Number of bonding 1, 2, 3, 4, 5. Only so much. Half into 5. 5 2s are 10 minus antibonding 1, 2, 4 electrons. Here 1 5, here 1 6. Trip the correct answer, Amma. Bond order is 2. Is it paramagnetic or diamagnetic, students? Very good. Tanmay, Sandra, correct answer, paramagnetic it is. Paramagnetic. It is paramagnetic. Now, in case of ions, how it will be? I want to write O2 plus for O2 plus. O2 plus 1, can you find out, students? O2 plus 1. O2 contains 16 electrons, right? Plus 1 means it lost 1 electron. 16 minus 1, 15 only you have to write. So here better write 16 minus 1. Plus means it lost 1 electron. So it contains total 15 electrons only. Find out the bond order, students. I'll arrange students. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px is equal to pi 2py. Keep two electrons here also. 1, 2, 3, 4, 5, 6, 7 over. One more electron will go to pi star 2px is equal to pi star 2py. Since we have only one electron, that one electron you keep in this. Avani correct answer. Now bond order is equal to half into number of bonding. 1, 2, 3, 4, 5, 10. Anti-bonding 2 plus 2, 4, 4 plus 1, 5. Bond order 2.5. No. Up to 18 electrons you can write Tanmay with this. Not more than this. Not more than that. Molecular orbital theory applicable till 18 electrons only. Tanmay. Afterwards you can't write. Next. O2 minus 1, can you find out, students? Is it paramagnetic or diamagnetic, students? My correct answer. Other students also. Is it paramagnetic or diamagnetic? If any orbital contain single electron, it is paramagnetic. Otherwise, diamagnetic. Tell me, para or dia. O2 contains 16 electron. Minus 1 means it gain one more electron. So 16 plus 1, 17 electrons. So 17 electrons arranged in this order and tell me what is the bond order. 1, 2, 3, 4, 5, 6, 7, 8. 16 plus 1, 17. Yeah. Bond order we'll see. Half into number of bonding. 1, 2, 3, 4, 5, 10. Minus 1, 2. Means 2, 2 is 4. 2 plus 2, 4. 4 plus 2, 6 plus 1, 7. 3 by 2, no? 1.5 is the bond order. Is it paramagnetic or diamagnetic? Paramagnetic. Since unpaired electron is there. Next, O2 minus 2. O2 minus 2 means how many electrons? 16 plus 2. 18 electrons you have to arrange. Tell me the bond order and magnetic nature, students. Bond order and magnetic nature. One electron you increase. Thinking like ISRO scientist. Pi star 2px2. 2 electrons are there. No? Here only one electron is there. No? That also will be paired. What is there? Yeah, Stevani. Now, after asking only they are sending. Without asking, they won't send. They have so much self-respect. What to do? 1, 2, 3, 4, 5, 10. Minus anti-bonding. 2, 4. 4 plus 4, 8. So here bond order how much? 1. No unpaired orbitals. So it is diamagnetic. Diamagnetic. You can do it for N2 plus, N2 minus, N2 N2 plus N2 minus 1 only, not more than that. You can do it for that also. Now, if I write clearly O2 plus 1, O2, O2 minus 1, O2 minus 2. Bond orders will write it together. How much students here? Bond order 2.5 we got. Here 2. Here 1.5. Here 1. Magnetic nature, if you see, paramagnetic, 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 diamagnetic, diamagnetic. Next, one more thing, one more point, student. If they ask which is stable, stability is directly proportional to bond order. One thing. One more point, these all things note down. Bond energy, bond dissociation energy. Bond dissociation energy means energy required to break the bond. Energy required to break the bond between atoms. Bond energy is directly proportional to bond order. If number of bonds increases, amount of energy required also increases to break. So which is having more bond energy? If they ask which is having higher bond order. And one more point, actually bond order I should have kept this side, left side. While copying, you do one thing, bond order you put left side, otherwise I'll only do here. Bond order is directly proportional to stability. Bond order is directly proportional to bond dissociation energy. Next one, bond order is inversely proportional to bond length. So all these questions you can answer by knowing bond order. Okay, these points keep in mind. Okay, sir, if we forget this energy order, entire thing will go now. How to remember? Sometimes we may forget. To avoid those problems, I am going to give one simple technique, one table. It gives a lot of information and easy also. You can to remember, including magnetic nature. I will give. This one table gives a lot of information. Copy the students. Here, number of electrons you take. One column. Bond order, one more column. Total to make it 3 columns. And last one is magnetic nature. Okay. Number of electrons from 10 I will take up to 9 and all easy only. Sigma 1 is 2, sigma star 1 is 2, same model. Bond order is 1. 11 electrons, bond order is 1.5. If you write also, you will get same thing. If system contains 2 electrons, bond order is 2. If system contains 13 electrons, 2.5. If system contains 14 electrons, 3. If system contains 15 electrons, 2.5. See students, up to 3, bond order increased. Again it is decreasing by 0.5, 0.5. Only so much. You no need to remember this energy order and all. Aram you can save the time also. 16, 2, again decrease. 17, 1.5. 18, 1. If you write electronic configuration, arrange electrons also, you will get the same. Next, 12 14, 18 electron systems are only diamagnetic. Rest all are paramagnetic. You can write magnetic nature also in simple way. 14 electrons, no? It is diamagnetic. Nitrogen example. Para and dia. 12, 14, 18 electrons. You remember like this. 2 4s are 8. 2 4s are 8. Copy it, students. Done, students. So now we'll apply for the molecules what and all we did so far. O2, O2 plus. It is very simple technique. You can save a lot of time in examination. O2, O2 minus 1, O2 minus 2. Here O2 plus contain how many electrons? 15. Here 16, 17, 18. 15 electrons bond order is 2.5. 16 electrons bond order is 2. Just decrease 0.5, 0.5, 2. Here 17 electrons bond order is 1.5. 18 electrons bond order is 1 from the table. Understood, students? Same thing we got, we checked while when we are using this one. Yeah, by using energy order also we got the same thing. Check once. 2.5. And magnetic nature, 15 electrons paramagnetic, 16 electrons paramagnetic, 17 paramagnetic, 18 diamagnetic. Easy? Even for heteroatomic molecules also you can apply. CO is there, carbon monoxide. How to take number of electrons? Carbon contains 6 electrons since it is atomic number 6. Oxygen contains 8 electrons since its atomic number 8. So total 14. 14 electrons means bond order is 3. Bond order is 3. 14 electrons magnetic nature, diamagnetic. Clear, students? Any doubt in this? So molecular orbital theory explains up to 18 electrons. This table also explains up to 18 electrons. Bond order and bond magnetic nature. If you know bond order, you can find out bond length. You can find out bond dissociation energy. You can also find out stability. Okay, students. This is the chemical bonding topic. So main topics you need to prepare: hybridization, Vesper theory. Maximum I have given students. You appear in NEET examination from chemical bonding, whatever the question they ask, you can answer in school standard only.